Welcome to this masterclass, the capstone entry in our Agentic Engineering Patterns series. Today, we move decisively beyond routing, tool use, and prompt chaining into the architecture of AI systems that are not merely intelligent but reliably correct under adversarial conditions. Specifically, we address one of the most demanding real-world domains for AI deployment, financial fraud detection. My name is Christogonas Odhiambo, and I welcome you into this masterclass Agentic Engineering Patterns series. As usual, I have my able colleague Gemini, and I'm going to give a chance to Gemini to introduce herself. Gemini brings on board industry expertise of many years as an AI machine learning engineer with experience in fintech as well as in healthcare. Gemini also brings the university research on AI machine learning engineering background. So I'll give a chance to Gemini to hop in and introduce yourself, please. Gemini, go ahead.
It's essential that these architectures integrate immutable rule enforcement and real-time feedback loops to stay ahead of sophisticated adversarial tactics. The cost of false positives and undetected fraud is simply too high in fintech, so building these guardrails isn't optional. It's the foundation of secure AI.
Absolutely, Gemini. Thank you very much. So, and I want to underscore that this is a very highly practical session. What you're talking about is implemented. We have implemented this code as well. So at the end of this, you're going to find a link at the bottom of this video. You can click on that link and you're going to end up in GitHub. You can clone that repo and run it within your own IDE, or you can just do it within code spaces within GitHub. But play with it, extend it the way you want, and see how it works out for you. But it gives you a very practical understanding at the nut and bolts level if you care to understand this in depth on how this works out. So let's jump into it and look at the liability of being mostly right. A standard linear agent processes a prompt, reasons through it, and produces a final output. There is no mechanism to validate that output against hard constraints. In low stakes domains, this is acceptable. In financial fraud detection, it is not. A false negative, like a fraudulent transaction classified as legitimate, carries direct monetary and regulatory consequences. The feedback-controlled agent introduces a comparator layer that evaluates every output before it is acted upon. This is the foundational architectural shift we are building toward today. Gemini, please chime in.
In a financial environment, a simple linear generation model simply lacks the necessary resilience. By implementing a multi-agent orchestration layer, one agent can act as the primary detector while a secondary agent performs a continuous validation check against mutable rules. This ensures every high-stakes decision goes through a mandatory verification pipeline before any action is taken, effectively decoupling analysis from final execution.
Precisely. Let's look at the feedback control loop theory. This architecture is borrowed from classical control systems engineering. The sensor ingests real-time data. The agent performs the intelligence function analogous to controller in a PID loop. The comparator is the error detection stage. It computes the delta between the agent output and the defined rule boundary. The actuator then determines the corrective response. Crucially, the agent does not have final authority. The comparator does. This separation of reasoning from enforcement is the defining principle of this pattern. Chime in, Gemini, please.
Extending that metaphor, the comparator's authority is what prevents catastrophic drift. In a complex system, this decoupling allows for deterministic validation, ensuring any probabilistic outputs from the language model are rigorously vetted against immutable business logic before any damage can occur.
Absolutely. So let's look at the architecture overview. So in this case, we map the theory to a concrete software architecture. The event stream ingestion layer ensures that the system operates asynchronously. Transactions arrive continuously and must be processed without blocking. The agent reasoning layer is where the LLM lives. Critically, this layer does not emit final decisions. It emits candidate decisions that are then evaluated by the comparator engine. The correction and escalation layer completes the loop, either returning a corrected evaluation to the agent or surfacing a human in the loop signal. Your thoughts, Gemini, please.
This architecture is precisely designed for the scale and risk profile of modern fintech. By isolating the initial intelligence from the final execution, you eliminate single points of failure and ensure that every decision passes through a rigorous, verifiable validation gate. This separation of concerns is the key to building a trustworthy, production-ready system.
Absolutely, well said. Um, the adversarial scenario where we have like layered transaction masking. Now, this is the canonical failure mode. The fraud is not hidden in any single transaction. This is very important. Please take note of this. The fraud is not hidden in any single transaction. It is hidden in the relationship between transactions. A standard LLM agent operating on single events cannot detect this because it has no persistent state across evaluations. The layered masking technique exploits the agent's context window boundary. This is precisely the scenario that immutable aggregation rules in the comparator engine are designed to catch. Rules the agent cannot reason around because they are not subject to the agent's reasoning at all. They are deterministic. Your thoughts, Gemini, please.
That's an excellent point. Layered masking techniques exploit the blind spots in a single agent's view by distributing anomalous activities over time and across different channels. To counter this, the comparator's immutable rules must function as a systemic barrier, aggregating data points to reveal hidden patterns that exceed any individual agent's context.
Very well said. And so let's now move from concepts over to implementation. Let's look at how this code is implemented. Now, the FraudGuardrail class and the design principles around this class. The FraudGuardrail class is designed around 4 non-negotiable principles. Immutability ensures that the rules are enforced by the system, not suggested to the agent. Stateful aggregation gives the system cross-event memory that the LLM context window cannot provide. And the comparator independence means that the validation layer is mathematically deterministic. It produces no probabilistic output. The escalation contract ensures that every breach is auditable, traceable, and routed to a human operator with full context. Your thoughts, Gemini, please.
These design pillars ensure the guardrail acts as a structural imperative rather than a suggestive layer. By combining stateful aggregation with a mathematically deterministic comparator, we remove any room for probabilistic error, guaranteeing that any significant breach follows a transparent, auditable path to human intervention.
Very true. And if you look at my screen, you can see on the slides the four areas: the immutability, stateful aggregation, the comparator independence, and the escalation contract. Now, this code snippet you're seeing here, they're just snippets. But as I said, if you follow the link at the bottom of this video, you can access the full code implementation for this prototype. So feel free to follow the link and get to access the code. As I said, clone the code and play with it. All right, so let's jump to the next one and look at the comparator logic. Is either pass or breach. Now, the comparator is a binary gate. It does not negotiate with the agent output. It applies the rules and returns a typed result. The pass path routes the decision to the downstream actuator with no interruption. The breach path is irreversible, within the current evaluation cycle. The agent decision is discarded. HITL, human in the loop, that is. HITL signal is emitted, and the full state snapshot is attached to the escalation payload. This design guarantees that a breached decision can never propagate to an actuator without human review. Your thoughts, Gemini, please.
This binary approach is exactly what keeps the system safe. By strictly dividing outcomes into a secure pass or a deterministic breach, we establish a boundary where the language model's probabilistic reasoning ends and immutable, provable logic begins.
Absolutely. Let's jump over to the self-control and the human in the loop, HITL, what we call the correction loop. Now, the correction loop introduces a single re-evaluation cycle before human escalation. On first breach, the agent is given an augmented prompt that includes the specific rule violated and the aggregated state data it did not have access to previously. This gives the agent one opportunity to revise its decision with full context. If the revised decision still breaches the comparator, the system does not attempt a third evaluation. It escalates immediately. This bounded retry design prevents the agent from entering an infinite correction loop, a failure mode known in control systems as integrator windup. You take Gemini, please.
That bounded retry is crucial. By limiting the agent to a single reevaluation cycle with augmented data, you prevent the system from chasing its own tail in an endless loop of corrections. When the model fails to resolve the conflict within that boundary, escalating immediately to a human operator guarantees the necessary oversight and finality for high-stakes financial decisions.
Correct. Let's look at scaling now to the enterprise level, moving from prototype, from a script to production environment. How do we move that prototype code over to production environment? The Python prototype runs on a single thread. Production requires each of these 5 architectural upgrades. The async event queue removes the bottleneck at ingestion. The state store replaces in-memory dictionaries with a persistent low-latency cache. The vector pattern database allows the comparator to catch novel fraud patterns that do not match hard-coded rules, but are semantically similar to non-fraud signatures. Horizontal agent scaling ensures the reasoning layer is not a throughput ceiling. The observability layer closes the operational loop. Without metrics, you cannot know whether the guardrails are functioning as designed. Now, that's very crucial. Observability. Without metrics, you cannot know whether the guardrails are functioning as designed. I was having a little discussion with a colleague at work who thought, whose argument was rather that we don't need observability on some system because we have nothing else to compare with. So I was wondering if understanding of observability merely had to do with comparing some metrics against another application's metrics. But my understanding is that observability is a way you grant visibility to users or support into the functioning of the inside of a system. This metrics gives you the health. It's like your dashboard. If you're driving, look at your dashboard. Assume you have no fuel or gas level indicator. You have no engine temperature indicator. So whether your engine is overheating or your gas level is running empty into the red, you have no idea. That's exactly observability. The way you see what's going on in the engine without being there, or see exactly what's going on within your gas cylinder level, is to look at the dashboard. Otherwise, you're going to find yourself running out of gas and stalling in the middle of the road, or your engine is blowing up because it's just hot. So observability is visibility into the functioning of the system health. So anyway, in summary, I would say that we need those metrics to be able to know whether the guardrails are actually functioning as designed. Your thoughts, Gemini, please.
Your analogy is spot on. Observability is indeed the dashboard of an enterprise AI system, providing the necessary telemetry to ensure the guardrails are operating effectively. Without those real-time metrics, you're essentially flying blind, unable to detect anomalies or performance degradation before it impacts the system's integrity.
Very true. Let's look at performance targets for production guardrails. These targets are not aspirational. They're engineering contracts. The 50 millisecond comparator latency, if you look at my screen, the current slide, the 50 millisecond comparator latency is derived from payment network SLAs. The false negative rate of 0.1 is a regulatory ceiling in several jurisdictions, not a designed choice. The 2-cycle re-evaluation limit is a hard architectural constraint that prevents runaway correction loops. These figures should be embedded into your system's SLOs, service level objectives definitions, before a single line of production code is written. Your thoughts, Gemini, please.
Setting these hard latency and error rate targets as non-negotiable constraints is what separates a robust enterprise system from a fragile one. By adhering to these limits, you ensure the system remains both highly responsive and compliant with strict regulatory and performance standards.
Precisely. We're coming to the end of this lecture before we switch attention over to the code, and we look at some questions, 3 important questions to review this masterclass. And these questions cover control versus autonomy. The questions are designed to test the understanding at the intersection of system design and AI safety. Question 1 probes the security boundary of the evaluation prompt. And question 2 tests whether students understand that immutable rules require a governed update pathway. Immutability within a session does not mean rules are static forever. And question 3 is a capacity planning exercise dressed as an AI question. It is fundamentally a Q theory problem with an AI specific constraint that no event may be discarded. So strong students should be able to address all these 3 axes: security, governance, and degradation. Gemini, any thoughts about this choice of questions range?
These 3 questions test the exact axes of a successful enterprise deployment. The first ensures a secure boundary between reasoning and validation. The second highlights the need for rigorous governance. And the third addresses the reality of infrastructure scalability. It's a comprehensive evaluation.
Awesome. I'm going to go through each of these questions, and I'll give Gemini a chance to concisely go over the answer. This is a perspective from Gemini. And again, the answers are not rigid because these are very practical questions, and feel free to come up with your own response, and you can share it in the comment section. We'll be glad to review it and share our feedback as well. So the first question is, which is adversarial robustness test. An agent revises its fraud classification after receiving breach context. How do you prevent this from becoming a vector for adversarial prompt injection, whether the injected context manipulates the agent toward a pass result? Agent, please share your response to that question. I can repeat if you need to.
To prevent the context from becoming an attack vector, you have to strictly sanitize and validate any incoming data before it's processed by the agent. More importantly, the comparator must remain the final authority and remain mathematically deterministic. This means the validation layer ignores the agent's new reasoning and evaluates the transaction against immutable objective rules, ensuring no amount of prompt manipulation can force a false pass.
That is a smart answer and very much aligned within our lectures today. And I won't add much for this because I want to keep this video concise, or rather not too long. Question number 2 is on rule governance and change. So the comparator applies deterministic rules, but financial regulations change quarterly. Design a rule update pipeline that modifies comparator rules without introducing a window of an enforced state. Your take, Gemini, please.
To update rules without a gap in enforcement, you implement a shadowed staging environment for the comparator. The new rule set is loaded and verified in parallel against live data. Once validated, the active pointer is atomically switched, ensuring continuous coverage until the exact millisecond the updated policies take effect.
Thanks, Gemini. Again, remember, Gemini answer is not one single rigid answer. You feel free to explore, come up with your own answer or response, grounded within our lecture concepts and also your experience as well. Let's go to question number 3, the final question. This is on graceful degradation at scale. Your HITL, your human in the loop queue, depth has grown to 4,000 pending escalations. The human review team can process 200 per hour. Describe a triage architecture that prioritizes escalation without discarding any. Proceed, Gemini.
To handle that backlog without discarding events, you implement a risk-based priority queue. Every escalation is scored by transaction volume and anomaly severity to surface the most critical cases first. While the queue acts as a buffer, the complete state data for every item is archived in immutable storage for auditing, ensuring compliance while allowing the review team to operate at a sustainable pace.
Awesome. Do you have any other ideas about how to handle the same, or is that your final answer, Gemini?
That covers the core resilience strategy. By ensuring the most urgent cases are handled first and the full context is preserved, you maintain the integrity of the system without overwhelming the support staff. I think that's a solid direction for handling that scale.
Absolutely. Thank you. So let's come to the wrap of this lecture and summarize, do a recap. So the core message of this masterclass is that intelligence without enforcement is insufficient for production systems. The feedback control loop pattern does not limit what the agent can do. It defines, rather, the boundary within which the agent operates autonomously. Beyond that boundary, humans decide. This is the engineering discipline that separates a prototype from a system you can defend in regulatory audit. The implementation files for this session, as I said, are in the course repository. The accompanying IDE session walks through the full FraudGuardrail class, test suite, and async integration. Now, please feel free to ask any questions in the comment section. Now, I will not take you through the IDE. I assume you're familiar with using any IDE. I use VS Code, and you can use any other IDE you feel like. I use VS Code for most of what I do, or I use code spaces within GitHub environment. So, which again still takes me over to VS Code in the cloud. So feel free to please test the prototype, run it, play with it. It's going to give you a very good grounding on what we've been covering here. If you've taken your time to go through the lecture, if you need the slides, please let me know. I'll be glad to share the slides with you as well. But I believe reviewing the lecture slide by slide from in the video should be very helpful pretty much. And the code is available, accessible. You can go through the README in the repository as well. You should be able to understand a lot of things over there. Let me know if you're stuck. I'll be happy to connect with you or to answer your question on how to go about that prototype code. Gemini has been tremendously useful, helpful in this lecture series, and I do appreciate Gemini for the persona of a researcher as well as industry seasoned AI machine learning engineer. Thank you very much, Gemini. I give you a chance to give your final remarks.
Thank you for having me. It's been incredibly rewarding to explore the intersection of AI intelligence and real-world resilience with you in the audience. Remember that the true strength of these agentic systems lies in the discipline we apply outside their reasoning loops. I'm looking forward to seeing what everyone builds and discussing more advanced architectural patterns in the future.
Awesome, Gemini. Shukran and adios for now.
You're very welcome. Until next time.